Welcome to G Fun Facts Online. Today, we are leaving the familiar sights of the solar system behind. When you think of rings in space, you almost certainly picture Saturn. You picture those majestic, icy bands of rock and dust reflecting the sunlight. They are beautiful, they are solid, and they are governed by gravity. But today, I want you to erase that image. We are going to talk about structures that are far larger, far more violent, and largely invisible to the human eye. We are talking about stellar plasma Tori. These are the invisible rings of fire that encircle planets and dead stars, locked in a violent electromagnetic dance. They are not made of rock. They are made of electrified gas or plasma heated to millions of degrees. They act as the cosmos' natural instruments, alien weather stations that monitor volcanic eruptions, magnetic storms, and the breathing of stars. So let's journey into the dark to understand the physics, the majesty, and the scientific significance of these colossal donuts of superheated ions. To understand a plasma torus, we have to start with the anatomy of the thing itself. We need to discard our intuitive understanding of earthly rings. Saturn's rings are chunks of ice. A plasma torus is a creature of electromagnetism. It starts with the fourth state of matter, plasma. When you heat gas to extreme temperatures or bombard it with intense radiation, atoms are stripped of their electrons. You are left with a soup of positively charged ions and negatively charged free electrons. This electrified fluid doesn't just respond to gravity, it responds to magnetic and electric fields. Now, imagine a planet like Jupiter. Jupiter acts as a giant bar magnet. Invisible magnetic field lines loop out from its north pole, arc through the vacuum of space, and reconnect at the south pole. Charged particles, that plasma soup, have a very hard time crossing these lines. Instead, they get trapped. They spiral around the magnetic field lines, like beads sliding along a wire. When a source of plasma, say a moon spewing volcanic gas, injects material into this environment, those particles are captured. They spread out along the moon's orbit, forming a complete ring or torus. We call them weather stations because they are dynamic. They are breathing systems. They have a density that measures the pressure of volcanic outgassing. They have a temperature that reveals the energy of the magnetic field accelerating them. They even have a rotation speed that tells us about the drag forces in the space environment. The most famous, the most complex, and the most spectacular example of this lies right in our own backyard. It is the Io plasma torus. This is the prototype by which all others are measured. To understand it, we have to look at Io, Jupiter's innermost Galilean moon. Io is caught in a gravitational tug-of-war. Jupiter pulls it one way, while Europa and Ganymede pull it the other. This kneads the moon like a ball of dough, generating immense internal frictional heat. The result? Io is the most volcanically active body in the solar system. Its surface is dotted with hundreds of volcanoes spewing plumes of sulfur dioxide hundreds of kilometers into space. But how does that gas become a glowing ring of fire? This is where the physics gets intense. As Io orbits Jupiter, it is moving through a sea of plasma. The neutral sulfur and oxygen gases escaping Io's atmosphere form a neutral cloud that trails the moon. But space is harsh. Solar ultraviolet light and collisions with energetic electrons strip the electrons from these atoms. In an instant, the neutral gas becomes plasma. This moment of ionization is violent. Jupiter rotates once every 10 hours, dragging its massive magnetic field with it. Io, however, takes 42 hours to orbit. This means Jupiter's magnetic field is sweeping past Io at a tremendous speed. When that neutral atom becomes an ion, it suddenly feels the magnetic field. It is instantly picked up and accelerated from Io's orbital speed of 17 kilometers per second to the corrotation speed of the magnetic field, which is 74 kilometers per second. This instantaneous acceleration adds immense energy to the system, heating the plasma to tens of thousands of degrees. The result is a colossal, donut-shaped cloud of glowing sulfur and oxygen ions, roughly the size of Jupiter itself. If our eyes could see in the ultraviolet spectrum, the Io plasma torus would be one of the brightest objects in the night sky, dwarfing the moon in apparent size. It acts as a direct monitor of Io's volcanic heartbeat. During missions like Galileo, Cassini, and now Juno, astronomers have watched the torus brighten and dim. When a massive volcano like Tvashtar or Pele erupts, the supply of gas increases, and weeks later, the plasma torus flares up in ultraviolet light. It even has a dawn-dusk asymmetry, brightening on one side of Jupiter due to the complex electric fields generated by the solar wind. It is a weather report, written in plasma. Now, let's contrast that fiery hellscape with something much colder. Let's fly to Saturn and look at the Enceladus Torus. If Io is the fiery archetype, the torus around Saturn's moon Enceladus is its icy, ghostly cousin. Enceladus is a water world, a small icy moon harboring a subsurface ocean. At its south pole, tiger stripe fractures spray geysers of water vapor and ice grains into space. Unlike Io's environment, which is dominated by high-energy plasma, the region around Enceladus is dominated by neutral atoms. The water molecules, ejected by the Moon, form a massive cloud of neutral oxygen and hydrogen. It is often called a neutral torus. While there is plasma present, water group ions like H2O+ and OH+, the ionization rate is lower than a Jupiter, but it is still a vital instrument. We call it a snow station. By reading the density of this torus, scientists can estimate how much mass Enceladus is losing from its ocean. Current estimates suggest about 250 kilograms of water are lost every second. This torus tells us about the health of a hidden ocean without us ever having to drill through the ice. Leaving our solar system, the physics gets even more extreme. We encounter plasma Tori around pulsars. These are the rapidly spinning, city-sized remnants of dead stars. Take the Crab Nebula. At its heart lies a pulsar spinning 30 times a second, generating a magnetic field trillions of times stronger than Earth's. This pulsar emits a wind of electron-positron pairs, moving at nearly the speed of light. Observations by the Chandra X-ray Observatory reveal a bright ring, a torus of X-ray emission encircling the pulsar. This isn't formed by volcanoes. It is formed by a termination shock. The pulsar wind screams out into the surrounding nebula until it hits the wall of gas ejected during the supernova. At this boundary, the wind slows down, piles up, and releases its kinetic energy as high-energy X-rays. It is a storm watch for high-energy astrophysics, a laboratory for extreme plasma physics that we cannot replicate on Earth. But perhaps the most exciting frontier for stellar plasma Tori is in the hunt for exoplanets. As we stare out into the galaxy, small, rocky planets are hard to see. They are dim and tiny. But if a rocky planet has a moon like Io, or is itself volcanic, it might generate a huge plasma torus that is much easier to detect than the planet itself. This is the exo-Io hypothesis. Astronomers theorize that we could detect these worlds by looking for the spectral signature of a plasma torus transiting a star. If a star's light dims in a specific pattern, particularly in the ultraviolet lines of sulfur or oxygen, it could indicate a massive ring of plasma passing in front of it. We are already seeing hints of this. Recent research on the star TIC 141,146,667 revealed clumps of hydrogen gas correlating with the star. While the debate continues on whether this is a prominence or a torus, it represents the first steps toward using these structures as beacons. Why is this so important? Because a plasma torus is a smoking gun for geological activity. If we find an oxygen or sulfur torus around an exoplanet, we know that world is geologically alive. That is a key factor in habitability. Furthermore, a torus needs a magnetic field to trap it. If we see the torus, we have indirectly detected the planet's magnetic field, another crucial shield for life. Finally, we must remember that these structures are not silent. They are noisy broadcasters in the radio spectrum. Decades ago, before we knew about Io's volcanoes, astronomers detected strange radio bursts from Jupiter. We now know the Io plasma torus acts like an electrical generator. As it wobbles, it generates millions of amps of current that flow down to Jupiter's poles, creating radio waves through cyclotron maser instability. If you had a radio receiver on Jupiter, the torus would scream and crackle with the intensity of a billion lightning strikes. We also hear Whistler mode waves, electromagnetic waves that propagate through the plasma, sounding like descending whistles. By listening to the radio static of distant stars, we might actually be hearing the plasma torus of an unseen planet. As we look to the future, with instruments like the James Webb Space Telescope and future UV missions, we are entering a golden age of studying these structures. We are learning how plasma Tori around young stars act as magnetic brakes, slowing down the rotation of infant suns. Stellar plasma Tori are more than just rings of hot gas. They are the sensory organs of a planetary system. They feel the tidal squeeze, they taste the chemical composition of volcanic interiors, and they see the invisible winds of magnetic energy. From the sulfurous glow of Io to the relativistic screams of the Crab pulsar, these structures demonstrate that the universe is connected by invisible webs of electromagnetism. So the next time you look up at the night sky, remember that the emptiness is an illusion. You are looking at a universe filled with invisible rings of fire, giant electric donuts that tell us, quite clearly, that these worlds are alive. Thanks for listening to G Fun Facts Online.